Greetings everyone. In this video I'm going to be demonstrating a basic heap spray technique. Now in order to demo a heap spray, I first have to briefly describe what exactly a heap spray is. Essentially what it means is to saturate an area of the heap, or really any attacker-controlled area of memory, with desired code. What is desired code? Typically it consists of a NOP sled and shellcode or a ROP chain. Now the reason for doing so is that sometimes when exploit crafting, you can control a pointer such that it will jump to a predictable section of code, but not necessarily exactly where you want it to land. So the point of a heap spray is to saturate that area of memory with code such that you are statistically highly likely to land in your NOP sled, traverse that, and then execute your shellcode or ROP chain. So with that being said, let's take a look at some code that I can use to demonstrate this concept. Okay, so the code that I'm going to be using is here, and as usual you can find this in a link in the video description. This code is significantly more complicated than my previous code examples, so I'm going to walk through it. First I have my variable set up. I have my NOP size here, which for this demo I've set to 192. My shellcode size is set to 64. My payload size is simply the combination of the two. And then I have a statically allocated character array equal to payload size. My shellcode array for this demo is blank. I'll explain why in a second. And then here I have my array on the heap. You know it's on the heap because it's being dynamically allocated with malloc, and it is of size hex 6.4 million or whatever, which is 100 megs. I then have a int pointer, which will be a random address within the space that I'll explain later on. I have a call to mprotect here. Mprotect is a Linux syscall that changes the permissions on a section of memory, and I'll demonstrate what this does. This is the start of where I'm trying to change permissions. This is the size, and these are the permissions I intend to set. You'll note that the size is not exactly equal to the size of my heap buffer, and you'll see why in a minute. I then have two loops. The first loop will loop through payload size, which in this case is 256, 192 plus 64, and then if the loop counter is less than NOP size, it will set the byte of the payload to be x90 or a NOP, and if it's not, it will set it to my shellcode, which in this case for demo purposes is just hex 41 or a capital A. This second loop will loop through the entire allocated section of memory, all 100 megs of it, and set that buffer equal to essentially a repeating version of the payload. So it will set 256 bytes at a time, because that's the size of my payload, for the entire 100 megs of memory. Okay, ignore the commented out sections of code for now. I'll get to those in a minute and leave them commented out. So I'm going to go to my terminal here, and I'm going to compile my code, and you don't need to compile with any special flags. There you go. Now I'm going to fire this up in GDB so we can get cracking. So first I'm going to look at main here. I'm going to set 3 breakpoints just to demonstrate certain aspects of the code. The first breakpoint that I'm going to set is at malloc, which is at main plus 117. The second breakpoint I'm going to set is just after the call to mprotect, which is going to be at main plus 150. Finally, the third breakpoint I'm going to set is just before the call to free, which is at 263. Okay, now my breakpoint set, I'm going to run the program. Now, what I'm interested in looking at here is the memory segments that the program has allocated. So I'm going to run pda's vmmap command. So this should look familiar if you saw my previous video where we have the binary here, and then glibc, and then loader, and so on. Nothing particularly interesting there. So now I'm going to execute the next instruction, which is the malloc. And now I'm going to run vmmap again. And you're going to see we have 2 new segments here. We have a heap segment, and we have another memory map segment. I know this is new because if I go back to the previous display, I have my binary and then immediately followed by libc, whereas here I now have these 2 new segments now. Now, one of the unfortunate things about vmmap is that although it lists the start and ending address for the segments, it doesn't tell you the size, and I'm frankly quite too lazy to do math. Luckily, GDB has a built-in command called info proc mappings, which will tell me the exact size. And you'll note that the size of my mapped segment is 640,1000. This should look very familiar to you because in my code, this is 1,000 bytes on top of my allocated segment. Where does the extra 1,000 bytes come from? Honestly, I'm not quite sure. I assume it's overhead due to managing the memory map. But that is also why that is the size I have set in my mprotect call. Okay, so let's go back at the code here. So now I've found the memory map segment associated with the heap allocated buffer that I created. So now I'm going to continue this until just after the call to mprotect, and now I'm going to run vmmap again. And what you're going to see is that the permissions on this memory map segment changed. Now it's read, write, execute. You notice also that it turned red. It turned red because memory map segments are not supposed to have write and execute permissions. That is a giant security hole. However, with the mprotect call, I can set permissions to be whatever I damn well please. In this case, I pleased that it has all permissions, and now it does. So what that means is, once I write code to this segment, it will be executable. Pretty cool. Okay, finally, I'm going to continue this one more time, and now I'm just before the call to free. So now what I want to do is just demonstrate, just to show you that my code is in fact where I say. So this is the start of my heap segment, so I'm going to look at some data in it, like so. And so what you can see here is that I have the ending of my NOP sled and then my shellcode, and then here is the beginning of my next NOP sled. So you can extrapolate from here that this entire memory map segment is full of my carefully crafted NOP sled plus shellcode. Okay, that's all I wanted to show in GDB, so now let's take a look at those weirdly commented out sections. Okay, so now let's go back to our source code here, and I'm going to uncomment the first section of code only. So what this is doing is this is seeding my RNG, not very securely I'll grant you, but good enough for my purposes, and then this line. I'm going to admit that I stole this line blatantly from Stack Overflow, and this is some black magic fuckery that I'm not going to pretend to understand. What it does do is generate a 4-byte aligned random address within my heap buff. I'm then going to print that address and then print the contents of that address. So let's take a look at it. I'm going to save my code here. I'm going to go back to my terminal, and I'm going to recompile it and then run it. So when I run it, you see I get a random address within my segment, and then I print the contents of that address, and it's going to either be 90s or, eventually, come on, there we go, 41s. All right, makes sense, right? Simple enough. So now let's go back and let's take a look at the second section of code. So I'm going to recomment this and then uncomment this. Save it again. Okay, so here I am seeding my RNG again. I have counters for successes and failures, which I'll explain in a second, a number of attempts that I'm going to run through, and then my percentage success rate. So what is a success or failure? Well, remember that the point of a heap spray is to saturate a section of memory such that when you randomly jump to an address within that section of memory, you are statistically highly likely to land into your NOP sled and then traverse that into your shellcode or ROP chain. So in this case, what this loop is going to do here is loop through my number of attempts, which is 10,000, generate a random address, just like this line, and then if the contents of that address are 90s, or my NOP sled, that's going to be considered a success. If it's not, that's going to be considered a failure. And then here I have my determination of my success rate, which is the percentage, and then I print out the number of successes and failures. Okay, so I've saved it. Now I'll go back into my terminal and I will recompile it one more time and run it. And so we're going to see that we have 10,000 attempts, 7,517 successes, 2,483 failures, for a success rate of 75.17%. And if I run this multiple times, you're going to see that all the numbers hover around 75%. So where is the number coming from? If we go back to the code here, we'll see that my NOP size is 192 and my shellcode size is 64. 64 times 3 is 192, and my payload is equal to my NOPs and my shellcode. So my NOP size is 3 times bigger than my shellcode, thus it is 3 times more likely to land in my NOP sled than my shellcode, and thus leading to a 75% chance of success. This is pretty low. This is just for demonstration purposes. In a real-life exploit, you would want the percentage success to be much higher. But anyway, there you have it. That is how to do a very basic saturation of memory for the purpose of performing a heap spray. Thanks for watching.